Hi folks, welcome to tonight's review session for Calculus 2. We're going to be talking about volumes by the shell method along with volumes by the disk method. And we'll try and briefly touch on arc length and surface areas as well for solids. As always, if you have any questions, there's a question box over on the right hand side that you can kind of put your questions on at any point in time. And other than that, I'm going to go ahead and get started. And if you have questions along the way, always post them and I'll try and answer them as best I can. So we're going to begin by finding the volume of the solid obtained by rotating the region above f of x equals x squared plus 2 and below y equals 27 for 0 less than or equal to x less than or equal to 5 about the y-axis. And just to give us a visual as to what's going on here, I'll do a brief graph. So x squared plus 2, you've shifted the graph up 2 units. So you have this point sitting right here at 0, 2, and we've got a parabola, and then you have the line y equals 27 sitting right here. And so that means if we were to find that point, you have 27 equals x squared plus 2. And so notice that means 25 equals x squared. Since we are on the positive side, we don't have to worry about the plus or minus. We're just dealing with the positive side. So this is going to be x equals 5. So you have 5, 27. And we are rotating about the y-axis. Okay? So that just lets you know how we came up with those points. And notice the 5 corresponds to with this x being less than or equal to 5. So we have no funny business to worry about. Things line up quite nicely for us. So this is our region that we're looking at, and we're going to rotate it. Now usually what would happen before is we'd have this nice little disk, but we would need this equation to be, if we're revolving around the y-axis, we need it to be in terms of y. So the big change in things is we need to use the shell method. And what does the shell method say? Well, the shell method basically focuses on the idea of using cylindrical shells to calculate this. And so I'm putting 2 pi RH and then D, and then we'll put a question mark essentially. So what does the R stand for? This is the radius of the shell, and H stands for the height of the shell. And this D question mark will be X if revolving around y, axis, and y if revolving around the x-axis. That's an X, don't let your eyes fool you. And you might say, well, why is that? Well, if you take a shell, let's take a shell of some sort. So you have some shell kind of coming around here. Let's move that up here. And so there's obviously a tiny little thickness going on there. Now I drew a line in that front part. You can pretend they're scissors. So you have your scissors and you're going to cut along that line and unfold it. Well, what happens? Well, all of a sudden you get this little shape that looks kind of like a rectangle, except you have some thickness going on there. And this height of your cylinder, H, that's going to be right there. And the radius that we're talking about, well, notice when we cut it out, the length would be this distance around that circle. Okay, and the distance, the way we get that is the 2 pi r. And so that's what's happening. Now, the only difference is when we get to the functions themselves, we're going to have to use r in terms of things like x's and y's. And we're going to need to use the h's in terms of things like x's and y's. So what do we have here? Well, with our function, we have y equals x squared plus 2. We have the y equals 27, and all that sung and dance. Okay? But notice those are function values. So at the end of the day, here's what happens. If you're taking a strip that we're going to revolve into a shell, right? So this thing's getting revolved around the axis. So there's our inside, and then we have our outside going on right there. Same thing down below. So there's part of our random shells, and we're going to build up more and more shells, but as soon as we take that random shell, notice we're revolving around the y-axis. So what that means at the end of the day is we're going to do a 2 pi, and then whatever this junk is in here, but then we're going to need a dx. Okay? With that in mind, we need the radius of the circle. Now I know that isn't drawn perfectly centered, but so radius would be the distance from here to here. Well, what is that distance? That distance is just x. So that's 2 pi x. That's dealing with a radius. Now what's our height? Well, our height can be found with going from here to that value. So what would that be? Well, notice our top value. Another way we can do this is we can take the value from here to here, which is 27. Let me move this dx a little bit. And then we need to subtract off the other distance, which goes from here to here. And what is that distance? That distance is x squared plus 2. So minus the quantity x squared plus 2. Okay, and what are our bounds? Where do our x values range from? Well, they go from 0 to 5, and that's actually given to us in the problem. All right, 0 less than or equal to x less than or equal to 5. So now, what do we have? Well, we can pull the 2 pi out. We have an integral from 0 to 5 of, well, notice 27 minus, and then we'll have minus x squared, then minus 2, so that makes 25 minus x squared. Oh, I'm sorry, 25, I forgot to distribute the x there. 25x minus x cubed. Got a little bit ahead of myself there. So 25x minus x cubed, and then our dx. Okay, so what happens now, we can take the antiderivative. You get 2 pi. The antiderivative of 25x is 25x squared over 2. And then the antiderivative of x cubed will be x to the 4th over 4. And if you have any questions on that, please just let me know. Evaluated at 0 and 5. And so what does this become? Well, this equals 2 pi times, well, notice we can actually distribute that 2, well, yeah, we can distribute the 2 and make it pi times. Notice this becomes 25 times 5 squared once we distribute that 5. Minus, this would be 5 to the 4th. So 5 to the 4th over 2 now. Well, notice this is also 5 to the 4th in the first term. So you have 5 to the 4th minus 5 to the 1/2 5 to the 4th. So this equals pi times 1/2 times 5 to the 4th. Okay? So we came up with a nice answer. Now, what I want to kind of mention here is we have other methods for this solution. And let's kind of illustrate that. So remember the disk method. If we were to use the disk method, we need to put things, if we're revolving around the y-axis, we need to go in terms of y. So in that case, where do our y values range from? Well, if you notice in our graph, we have y going from 2 to 27. So we'll put our integral from 2 to 27. And now what we need, we're doing something slightly different here, is we're taking a disk of this thing. And so we want the full-on disk of some random point in our curve, right? And you get this kind of mimicking on it. That's supposed to touch this part. And so now what we need is we need to find the radius from here to here, and it goes pi times, what's that radius going to be? Well, we need it in terms of y, so in that case you get y minus 2 equals x squared, and since it's on the positive values for the x's, so we get x equals the positive square root of y minus 2. And that's the radius, so we got to take that radius, so square root of y minus 2, and we got to square that quantity. Okay, so now what does that become? Well, that just becomes, we can factor out the pi, we take an integral from 2 to 27 of y minus 2, oh, I forgot to put the dy there, so y minus 2 dy. So we see two different methods. Let's see if we come up with the same answer. If things go correctly, we should. So this becomes, we get pi times the quantity. Notice we have y squared over 2 minus 2y evaluated at 2 and 27. Okay, so this should equal pi times 27 squared all over 2 minus 2 times 27, and then subtract off, so that's our first term, and subtract off, we got to plug in 2 for our balance, so we get 2 squared over 2 minus 2 times 2. Okay, that might not look like anything like what we had up above. Let's make sure that it does actually work out to be that way. So let's see here. We could rewrite this as we have 27 times 27 all over 2 minus, we can make this 4 times 27 all over 2. And then we got to subtract off. Notice you get 2 minus 4, so that should be negative 2, I believe. Okay, so we go 27 minus 4. Notice we get 23. So this equals 23 times 27 all over 2, and then plus an extra 2. And then all this is times pi. Okay, now you might say that doesn't look anything like what we have up above. Well, let's see here. Maybe we can break that down a little further. 23 is 25 minus 2, and 27 is 25 plus 2 all over 2 plus 2, and then that's all multiplied by pi. That's a difference of squares. So what you have is this becomes 25 squared minus 2 squared, which is 4, all over 2, and then plus, notice if you write 2 as something over 2, it's 4 over 2. Notice your 4's cancel, we still have the pi out in front, and so we have 25 squared, so pi times 25 squared all over 2. And notice we had 1/2 5 to the 4th in the first case. This is 5 squared over 2, so 5 squared squared makes 5 to the 4th. So this is the same exact answer, pi times 1/2 times 5 to the 4th. And notice I didn't touch a calculator at all. We can do both of these in our head. That's kind of the main point, though. It doesn't matter which method we use, just sometimes one's easier than the other. Okay, so hopefully you see the usefulness of the shell method, along with it was an easy integral in terms of the disk method as well. Just the arithmetic was a little bit more intense. So moving forward, let's see how we work some other problems. We want to find the volume of the solid obtained by rotating the region bounded by y equals x squared, y equals 3x, about the line x equals 3. So when we're looking at this thing, this is going to be a little bit nastier. Y equals x squared is just a parabola. So we'll draw that parabola. And y equals 3x, notice it's going to be a straight line. Now, trying to determine which is on top and which is on bottom, what we should do first is figure out where they intersect. So y equals x squared and y equals 3x. Let's assume we have a system of equations. You set them equal to each other because we both have them in terms of y. You get 3x equals x squared, so that means 0 equals x squared minus 3x. And so 0 equals x times x minus 3. And what that tells us is that x equals 0 and 3 are our intersection points. So let's put just 0 and 3. Now you pick a number in between there, just plug it in. So if I plug in 1, for example, notice we get y equals 1 squared, so that would be 1 comma 1, versus the second one would be y equals 3 times 1, so 1, 3. So the line actually lies on top. And so hopefully that makes sense. If not, let me know. I'll be happy to clarify a little bit more. But so we're looking at this region enclosed right here. Okay, and once again we have y equals 3x on top and y equals x squared on the bottom. And we are rotating about the line x equals 3. So this is where we're rotating. Okay, so we have options, and we'll go through both in terms of the setup, and I'll kind of let you solve the easier of the integrals. So if we are using, well, actually I'll let you decide. What do you want to use, the shell method or the disk method first? So go ahead and write down what you prefer, and we'll kind of go from there. And the key is to set it up so we have an easy integral. That's the ideal situation. But we'll look at both. So we'll have a shell method and a disk method. Okay, so we'll start with the shell method, where we actually have that listed first. And so remember, we look for that 2 pi r times h, and what essentially in the 2 pi, I'm going to start pulling that out from here on out. So we have the 2 pi. Now, the thing that we're revolving, so we have some sort of shell right in the middle, and we're going to revolve this thing over to the other side. You get something that looks like this. And we also have the inside part. Inside part there. Okay. So first things first, we need to find this radius. So that's the distance from here. Well, actually, let me change the color. Okay, that's the distance from here to here. Right? So what is that distance? Well, what you know is that in general, the distance from here to here is just some x. So if that's x, and this whole distance all the way to that x equals 3 is 3, that means that this radius r equals 3 minus x. Okay, does that make sense? I hope so. If not, let me know. I'm happy to clarify a little bit more. So you have 3 minus x sitting right there. Now, the next piece, what we need to figure out is what is this height of this? Well, notice the top curve, right? That's given by, at that point, that's going to be the 3x. And the bottom curve is going to be x squared. So all you need is you have 3x minus x squared. And your integral goes from 0 to 3. And then we have a dx. Ta-da! That's it. That's all you need to do. That's your setup. Now the rest is going to be integration. We'll talk about that, but first let's take a look at the disk method and see what happens here. And this is going to be the beautiful thing when you're actually calculating these things. It doesn't matter which method you use. I mean, I'm not going to sit there and say, oh, you have to use this method. But sometimes integrals will be easier one way versus the other. So that's what I want you to be comfortable with, writing them both ways and kind of determining which method looks better. So the disk method, remember what that does is that takes, so if we're revolving around this thing, let me try and erase that real quick. So we got our idea there. So now that this method looks a little bit different, let me repair that just a little bit. So we have this, and we have that. Now, in order for us to do this, it's similar to revolving around the y-axis. So in that case, notice what's going to happen. Well, we're in the positive x-axis, so we get x equals the square root of y. right? No negative square root of y in this case. And then we get x equals, in our other scenario, y over 3. Okay? And what we're going to do is we're going to have a washer going on here. And what's our washer look like? Well, you get a certain disk like that, but then you're going to take out a disk in the middle like this. And we got to figure out those different radii, I guess you could say. So the first one, we go to the outermost disk, and we're going to do this pi times, and we're going to take each disk. So notice, where's our y value ranging? Our x values were pretty easy. You go x equals 0 to x equals 3. But what does that mean in terms of our y value? Where did they intersect? Well, this intersection point up here, that's going to be 3, 9. And you can just plug it into either equation. So our y ranges from 0 to y equals 9. So in that case, we have an integral from 0 to 9. And then where do we go from here? Well, we need to square the radius. So we're going to basically take the first radius, which would be the distance from this y equals 3x, or I'm sorry, x equals y over 3, to the line x equals 3. So you could take 3 minus, and then it would be y over 3, and we want to square that quantity. But then we need to subtract out, and we can do another integral, or you can just keep it all multiplied by pi, which would work just fine. We need to work on that second radius. So that radius from, let's do in a lighter blue again, from here to here. So what is that distance? Well, that distance is from 3, and we got to subtract off the, in this case, square root of y, and square that. And then take dy. So notice in the second one, we can square those things, but you're going to get quite a few terms. Versus the first one, if we just expand this polynomial, we should be in pretty good shape. And in fact, if you really wanted to be kind of clever about it, the first polynomial, we could do 2 pi, an integral from 0 to 3. Notice you could factor out an x, and you're left with 3 minus x. So essentially this becomes x times the quantity 3 minus x, that quantity squared dx. And we know how to expand that perfect square. So you get 2 pi, an integral from 0 to 3. And then this would be x, and let me just expand this out for us here. So you get 9 minus 6x plus x squared dx. And to write it a little bit simpler, you get 2 pi, and then an integral from 0 to 3 of 9x minus 6x squared, whoops, 6x squared, plus x cubed. And then we want to take the antiderivative with respect to x. Any questions thus far? Please let me know if so. Okay, so if that's the case, we'll go 2 pi, and then our first antiderivative. Oh, okay, so there's a question, can I explain the setup for the shell again? Don't have to walk through the graph, just from the equations. I feel like it's simple, but my brain is rejecting and making it more complicated. Okay, yeah, no problem. The whole trick to this, all I did in that, it does help. It's gonna be useful if you use the graphs. The first thing, if you're setting up the shell method, is you have to find where these things intersect. So you have to go y equals x squared, and y equals 3x. And understanding that since it's x equals 3 is like revolving around that y-axis, we're going to have things in terms of x. So the way we do this is we go x squared equals 3x, which implies that x squared minus 3x equals 0. And so that gives us our two bounds. And you have to be careful sometimes. Not always will the equations line up perfectly. But so you have x equals, well, I'll write out the factors here real quick. This is x times x minus 3. And so that means x equals 0 and 3 are your solutions. So that tells us right there the bounds. The reason why I like the graphs, that actually, I know you may not enjoy them, but it does help you visualize what that h is. That's the tricky part here, because you have to figure out what's on top, what's the top function, and what's the bottom function. And what you can do in here, you know that this is your interval. You have an interval 0, 3. And they aren't interchanging anymore, otherwise there'd be more intersection points. So if that's the case, what we do is plug in any number in between there. You can plug in x equals 2. I just chose x equals 1 into each equation. And so in the first equation we had 1, 1. In the second equation we had 1, 3. So what that said is that this is the top equation, the second equation. And so that means we have to figure out, in that case, the height equals, well, it would be the top equation, 3x, minus the bottom equation, which is x squared. Okay, let me know if there's any questions on how we figured out the height. In the radius, this is where I like to use the graph, because you have this shell that's being revolved around. The radius is the distance to that 3 point, right? But you know the other side of that distance is x. So when you have that, you have x being this distance here. That means that the rest of the distance has to be 3 minus x to get a total 3, because x plus what gives you 3? Well, x plus 3 minus x gives you 3. And so that means our radius, so this is where the height came in, right here. And our radius was this 3 minus x. The 2 pi, remember it's always 2 pi radius, that comes from the circumference of a shell. The dx is usually stands for the thickness, so you have a thickness there. All this comes from a volume of a rectangular solid, essentially. So that's what I was discussing on that first slide at the very beginning. So hopefully that makes sense. If not, let me know and I'll try and clear up another way. But I'd recommend the graphs are very beneficial if you can draw them, and that's the trick, is understanding the drawings of the graphs. I can't emphasize that enough. That's really where you start to wrap your head around them. So yeah, so it does take practice, I'll admit. The graphs do take a bit of practice, but a lot of these, especially like the ones with the x squareds, the x cubes, try and do that as much as possible. You can even bypass the graphs in some regards, as long as you can understand when you're revolving around things like x equals 3, you're going to have the 3 minus x be the radius. And so that's the tricky part for a lot of people, is, well, is it 3 plus, is it 3 minus? There's going to be cases, depending upon where that graph appears, what will happen. So for example, if I had taken the graph to be, say, y equals negative 3x, then I have to do, the radius would actually become 3 plus, essentially something like a 3 plus x, or an x plus 3, depending upon where you're at. So if I had x equals negative 3, it would be 3 plus x in that case. So just, you have to be careful on some of these in terms of what falls out. So that's why I actually prefer the graphs. There are ways to bypass them, but it does take a lot of practice. That's the big thing. These can be tricky. This is one of the trickier parts of Calc 2, to be honest with you. So if you were to take this antiderivative back to the integral, so we get 9x squared over 2 minus 2x cubed, and then plus 1/4 x to the 4th, evaluated at 0 and 3. Okay, so we can leave the pi out in front and make it a little bit easier on ourselves. Just multiply it on 3. So you get, first off, you get 9 times 3 squared minus, it becomes 4 because you have that extra 2 multiplied on 3, so 4 times 3 cubed, and then plus our 1/2 times 3 to the 4th. Okay, and then plugging in zeros is going to give 0 for all those terms. So at the end of the day, we get pi, and then this is 81, and that's the 3 to the 4th is 81, so you have 1/2 81. So what we have is 1/2 81 minus 4 times, did I do that right? Hold on, let me double check the antiderivative. So we have 9/2 x squared. oh, I'm sorry, I put 1/2 81. This is addition at the back end, so that should be, ooh, that's a big mistake there. That should be 3/2 81. Okay, feel a lot better there. I got nervous for a second. So we have 3/2 81 minus 4 times 27. And what you might be wondering is, why was I double checking that? I know that this is a volume, and the volume must be positive. Okay, so that's all. You can double check. If you ever come up with a negative solution, then you got a problem, right? So now this should be a little bit better. Another way we can approach this, we can write this as 9/2 times 27, and this is 8/2 times 27. And so your final answer, if you wanted to actually work it out, 9 minus 8 gives us 1/2 times 27, or 27/2. And so that's our final answer. And notice, once again, didn't have to use a calculator, right? So at the end of the day, you can leave it in terms of something like this line right here. That's good to go. That shows that you actually have the knowledge going on as well. So hopefully that clears up on this one. We'll try one that's a little bit trickier for a lot of people. So is if you have this region bounded by x squared plus y minus 3, that quantity squared equals 1. And if that's rotated about the x-axis, what's the volume of the resulting solid? This is part of the reason why we kind of like to use some of those results in terms of what's happening here. Because if you understand what's going on with this graph, so you go x squared, and then we go y minus 3 squared, and we have equals 1. What this means, this is a circle with center at 0, 3. So that's going to be 3 right there, and radius 1. So we have something like that. But then we're going to revolve around the x-axis. Well, notice, what shape do we make? Can you see what's coming here anytime soon? Tell me if you recognize that shape. If that graph looks familiar, let me know, because we can actually cut down on time in terms of what's about to happen. I can show you how quick this problem can be. Ah, very good. So Chelsea, you can send me an email just reminding me. You'll get a bonus point for that. So just saying that it's a torus, that does the trick. And actually, if you look at there's a previous video and a previous homework problem that talks about the volume of a torus. Okay, and so the volume of a torus I'll give the general scenario. So if you have a torus and then let's say the other circle, do not let your eyes fool you. That is a perfect circle sitting right there. So the distance from that center, let's call it capital R. But the distance, let's say, of this second circle is little r. Okay. What happens is you get the volume of this thing is 2 pi squared, and then you go capital R times little r. That's it. So if you actually look back, what actually happens is, well, notice our little r, the radius has to be 1, right? So little r equals 1, and then the capital R, well, that's this distance from, I know my center's kind of shifted here. I technically should have, let me do that. There we go. So my drawing isn't the greatest, but there's our center. From the center of the torus, that capital R is equal to 3. So my claim, and I'll show it, I'm not going to just leave it hanging. My claim is that this is going to be 6 pi squared. Done, right? Didn't even have to touch an integral. That's the beautiful thing. If you come up with a formula, you're good to go. Now let's assume I'm a mean person. I said, hey, calculate this thing. So how the heck do we do that? Well, you've seen a method where we use the first one. I think we did the disk method. All right, so I'll try and use the shell method just so we can get some practice with that. But I want you to understand that, hey, we have some results. We can use those results and build bigger things. So we have, once again, our circle right up here. Now, with us revolving around the x-axis, if we were using the disk method, we want things in terms of x, but since we don't, we'll have things in terms of the y values. So the cutoffs will be, for our y bounds, it will be here and here. Well, notice this is a circle with center at 3, so 0, 3. So the y values, if this is radius 1, that means it's 2 and 4. Let's say you didn't know that though, right? Say we wanted to figure out what that lowest bound is. Well, notice the x value equals 0. So here's all you have to do. You go 0 squared plus y minus 3 squared equals 1. Well, you take the square root. Notice you get plus or minus 1 equals y minus 3. And so you get y equals 3 plus or minus 1. And so notice, or that's a 1, sorry. So when you go 3 plus or minus 1, well, take 3 minus 1, you get y equals 2. 3 plus 1, y equals 4. Okay? So now all we need to do is break this up into the terms of the equations. And remember, you need a right equation and a left equation. Well, in that case, notice we need to solve for x in terms of y. So you get x equals 1 minus, well, first off, well, let me do the 1 minus. You get x squared equals 1 minus y minus 3, the quantity squared. But now what we need to do is do a plus or minus on that when we take the square root. Okay, so you get x equals plus or minus the square root of 1 minus the quantity y minus 3 squared. So a lot of work, but so just so you can see a visual what's happening, this side is x equals the positive square root of 1 minus the quantity y minus 3, that quantity squared. Whereas the other side, they'll do this in dark blue, so that would be x equals minus the square root of 1 minus y minus 3, the quantity squared. Okay, so even if you may not understand the pictures, but solving for x, that's all you need to do. And we're kind of getting ready to set up our bounds. We want to try and figure out if we take this little rectangle here that's shaded in, and we're revolving that around, right, into some little piece over here. Right, we have some other shape going on. Okay, so here's our cylinder. Now we need two pieces. So we'll have the 2 pi, since we're using our shell method. Our integral goes from what to what? Well, we already found those bounds. Those bounds are down below just by setting the x value equal to 0. So we go from 2 to 4. Now this will look kind of crazy, but we'll start to simplify this thing really quickly. So the radius is just the height up to that value. Notice that's just the y value. So 2 pi y. Okay? And then times, well, we need to go from right to left. So you start from this side over here, and we need to get that distance. So what is this distance? Because that's essentially our height of our rectangular solid. And the way we get that is take the rightmost value, so the square root of 1 minus y minus 3, the quantity squared, and subtract the leftmost value, which would be negative square root of 1 minus y minus 3, the quantity squared. And then we're going to take all that thing and slap a dy at the end of it. Okay, so this becomes 2 pi times the integral from 2 to 4. It looks really nasty right now, right? But if you notice, you go minus a minus, that makes a plus, and they're both the same thing. They're both square roots. So you can write this as 2y times the square root of 1 minus y minus 3, the quantity squared, dy. Okay? So since we have that, hopefully, let me know if there's any questions on that maneuver. Now we have an integral that we're pretty close to being able to solve, but it'll need a little bit more work, a little bit more polishing up here. And so that's what we'll do. In order to solve this integral, we'll probably want to use a u substitution. Not the only method that you can use, but it's probably going to be the best route and the cleanest route for us. So you go u equals y minus 3, and that means du equals dy. But notice that does not account for, oh, and by the way, just in case, if you're looking for notes, the radius was the y, this was the height, and then the dy is the thickness of the shell. In case you're wanting to keep notes in terms of separating each of these. So moving forward on this bit, what happens? Well, you have the u, you have the du, so we could write the square root of 1 minus u squared, but we have that extra y, and so the way to kind of account for that, we could solve for y in this second equation, y equals u plus 3. So this is a different sort of substitution. Notice we can take this 2 and apply it outside because it's just a constant, so you have 4 pi. I'm going to come back and talk about the bounds in just a second. The y, we just said, is u plus 3. And we have square root of 1 minus u squared. And then we have dy can be replaced with du. Now, with this, you can do it one of two ways. I would recommend changing the bounds. Otherwise, you're going to have extra steps in the integral. And so, in this case, changing the bounds, your bounds were 2 and 4, so you plug those in for the y value right here. Okay, that way we won't have to plug it in at the end. So you plug it in, you plug in 2, you get 2, actually I'll write it out. So you get 2 minus 3, and in the top case you get 4 minus 3. So this makes a new integral. And it makes 2 new integrals, in fact. We have 4 pi, and we'll worry about those 2 new integrals. I'll erase that piece so we can have enough room. So 4 pi, and then we have an integral from negative 1 to 1 of u times the square root of 1 minus u squared du. And then plus, notice the 3 is just a constant, so we can make it 12 pi times the integral from negative 1 to 1 of square root of 1 minus u squared du. Okay? So here's the trick to this in terms of how we can handle this. It goes back to even and odd functions. This function right here, if you notice, that is an odd function, meaning f of negative u equals negative f of u. And there's a result. If f is an odd function, and this is a beautiful result in terms of you get negative a to a of f of, doesn't have to be x, it could be u, it could be whatever value it is. But if it's an odd function, that integral always equals 0. And so this whole shindig right here equals 0. Done. Don't even have to look at the antiderivative. Okay. If you want to, use another, we'll call it a w substitution. You can check it out and see that it actually does cancel out and make it equal to 0. But now we're starting to cut down some time. And so with our second equation, what's happened is, yeah, woohoo, that's right. I agree. It's using those sorts of things, odd functions comes in handy left and right. So this one is not an odd function. It's actually an even function. But and there's ways to deal with even functions as well. But what happens is we can work with this thing quite nicely. Did I have 12 pi? Hold on one second. I'm sorry. U plus 3. Yeah. Okay. So we're good. So what happens with this equation, if I have the u-axis be right here, this is just the top half of a circle. So it's negative 1 to 1, and all I need is the area right here. So notice a full circle will be pi r squared. But in this case, we have 12 pi, and it's only a half circle, so we'll take 1/2 pi times our radius, which is 1, squared. So notice I didn't have to find any antiderivatives here. And what are we left with? 12 times 1/2 gives us 6, and then we have pi times pi makes pi squared. And notice that answer matched our original answer just by knowing the volume of a torus. So that's the beautiful thing, and I mean, if you see the circle and it's not revolving on itself, you're actually getting the answer either way, right? So it's just visualizing what's going on, and this is the usefulness of understanding what the graph looks like and what happens when you're revolving that thing around there. Okay, so this is another one kind of tying in, and we're going to start to see, okay, we can use things like integration by parts and stuff like that along the way. So you may not know this graph off the top of your head. That's fine. There's a way to do this one as well. But the thing to make note of, actually what this does is pi over 2x, that changes the period. And so you're left with, if you start at 0, you plug it in, you get 1. So you start with some value up here. And then that's 1 right there. And on the second part, when you plug in x equals 1, you're basically cut down the period, and you get cosine of pi over 2, which goes to 0. So you get a curve that looks like that. So yeah, you're allowed to use the volume of the torus if you can recognize that, unless I say prove the volume of the torus is such and such. That would be the only case where I want to see the steps. But yeah, if I just give you some equation and you find out, oh, this is going to be a torus, you're done in a matter of seconds. So you can use that volume. And as I mentioned, you're allowed to page your notes, so it shouldn't be a big deal. And the question was, would we have to show you the proof? No, if I just give you a problem, say calculate this volume, I don't care what method you use. Unless I say prove that that would be the only case where you actually have to prove it. So keep that in mind. The more you know graphically and things like that, the more you can use them. So alright, so for this one, this is the y equals cosine of pi times x over 2. And we want to revolve this thing around the y-axis. So we're going to be doing, I won't even draw the shell, I'll just draw like the sliver of the shell. And so what happens? Well, we have this distance is what we're looking for as the radius. That's the radius. And then in that case, we get r equals our x value. So our integral becomes 2 pi times the integral from 0 to 1 is our bounds. Because we started at x equals 0, we go all the way to 1. And we get x. And now all we need to do is figure out the height. Well, the height is just going to be the function value, right? Because we have that little rectangle goes all the way up to where the function ends. So cosine of pi x over 2. And then we slap on a dx. So that part, in terms of the setup, it was one of the easier ones for us. But what makes this problem a little bit more difficult is that we have to use integration by parts in order to integrate this thing. And it might be easier. I'm going to just slightly make a minor change to the way we write that second one. It can confuse some people with the pi and the x up in the numerator, so I'm going to write it as pi over 2x. Same thing, just written slightly differently. So in order to use integration by parts, usually we want to get rid of that x, so we let u equal to x. That means du equals dx. So that means dv has to equal cosine of pi over 2 times x dx, right? So finding that antiderivative, you may or may not know it, but I'll kind of give you a general idea. If you have cosine of ax and you want to take an integral of that, right? You can let u equal to ax, then du over a essentially equals dx. And so you have to pull that 1 over a out. So this thing becomes 1 over a sine of ax plus some constant c. So we drop the constant c though when we're using integration by parts. So the 1 over a is 1 over pi over 2. So the easier way for us to look at this is 2 over pi sine of pi over 2 times x. Oops, drop the dx. Sorry about that. Okay. Let me know if that trips you up. I'll be happy to kind of clarify a little bit more. So this thing, this integral becomes 2 pi times, now it goes u times v, so we got x times 2 over pi sine of pi over 2 times x, and then we're going to be evaluating that thing at 0 and 1. and then minus the integral of, and it goes v du, so we'll still have the same bounds, 0 and 1, and then we have 2 over pi sine of pi over 2x dx, and that will close off right there. Okay, so I'm going to erase that piece. And I want to brush this up just slightly, make it look a little bit nicer. Notice we have a pi here sitting out in front. We're going to multiply that pi and that 2 on through, and to brush it up a little bit more, so we get 4x, because the pi's would cancel in that first case, 4x sine of pi over 2x, evaluated at 0 and 1. Minus, so when we multiply 2 pi times 2 over pi, notice we're left with 4 times the integral of sine of pi over 2 times x dx. Now the sine of ax would be actually the negative cosine. Oh, I forgot to put it in the 0, 1 there. Negative 1 over a cosine of ax. So this thing equals, let's start plugging in our first bounds. So we get 4 times 1 times sine of pi over 2 minus, and notice you have 4 times 0 times sine of 0. It doesn't matter what sine of 0 is, even though it is 0. We're good to go there. But so then we have minus, now taking that antiderivative, we'll have 4 times, it goes negative 2 over pi cosine of pi over 2 times x, evaluated at 0 and 1. Okay. If there's any questions on that, please let me know. So now what happens? Well, sine of pi over 2, that equals 1. So the first part, all this junk, this becomes 4. Minus a minus, we can make this plus, and then we'll go 4 times 2 makes 8 over pi times our cosine. So now we just got to plug in the values. Cosine of pi over 2 minus cosine of 0. And so this whole thing equals 4. Cosine of pi over 2 is 0, and cosine of 0 is 1. Okay? And so that means 8 over pi times negative 1, that would be minus 8 over pi. And that's our final answer. You could do this the other way in terms of finding the arc cosine and work with that. That's kind of a nightmare, though, to be honest with you. So I would highly recommend this method, even with the integration by parts working here for you. So yeah, okay, so the hardest part was finding the v, right? Okay, so let's go through that. I'm going to do that in pink then this time. So if we have the dv being cosine, so that was where I just used a general a. I just knew what was going to happen with the constant. Let's just calculate the antiderivative. You could don't confuse it with the u down below, but you go u equals pi over 2. That means pi over 2 times x. That means du equals just pi over 2 dx. But notice we have dx in our equation, so that means dx equals du divided by pi over 2. But another way for us to write that, and probably a better way for us to write that, is 2 over pi times du. Right? Because when you divide by a fraction, it's the same as multiplying by its reciprocal. So what does that make? Well, that makes our integral, we have cosine of u, and then it goes 2 over pi times du. And so you can pull the 2 over pi out in front, and we're left with just the antiderivative of cosine of u, which is just sine of u. And then we know what sine of u is, so you get 2 over pi times sine of pi over 2 times x plus c. Now the big thing, what I was kind of mentioning, is, in general, notice I said 2 over pi times sine of pi over 2x. If you have an a in here, so whatever, right, if this is, say, a capital B, then what that would equal in that case would be the 1 over b times sine of bx plus c. It's just some constant. So as long as you can find the reciprocal of whatever constant appears in there, you're done. And so that's the more general formula. So if on the next problem, say I tossed in cosine of 7/4 x, and you want to find the antiderivative of that, well, then you do 4/7 sine of 7/4 x. So you can generalize that as much as you want. Okay, so hopefully that makes sense on that part. All right, if not, let me know, please. I'll be happy to go back and demonstrate a little bit more too. So now this is where algebra gets, yeah, you're welcome. So the algebra gets a lot tougher coming up in arc length and surface area, and that's a lot of the problems. I mean, it was mostly algebra. So the calculus, just finding and setting up the integrals, hopefully that gets easier and easier over time. The algebra will be the trick, and this is one case where it is. So the arc length, if you have some curve, right? So let's say we have some function here, f of x, right? And we have some starting point with a value here, a, and another value here, b. How in the heck do we calculate this distance, right? Because it's not smooth, it's not a straight line or anything like that. And that's where calculus comes involved again. So the proof, you can look at the proof in your book. It talks about the mean value theorem, and you break these into smaller and smaller intervals and kind of use like a Riemann sum. It's not, the proof isn't horrible, but it's not necessary as long as you know the formula. And when you think about it, think of a coastline. That thing goes, when we're measuring distance along a coastline, I mean, your coastlines are going zigzagging in and out and all over the place, right? And so we don't have smooth, straight lines. How do we measure those things? And so we use some tools, and it starts with calculus. It builds up even higher than that. And that's what we're going to do. So on this stuff, what we're doing is finding the length of the curve. And then you'll see this generalized to surface area, right? So if you notice, what we need is we need the derivative to be continuous on a given interval, and we're going to square that derivative. So first off, we need, instead of f prime, I'll just write this as dy dx. They mean the same thing in this case. So what's the derivative of this function? Well, notice it's 4x cubed over 8 plus. This second part can be written as 1/4 x to the negative 2. So notice that becomes 1/4 times negative 2x to the negative 3. Okay, just to brush that up a little bit, because all we were using was the power rule on the derivatives. We have, this is 1/2 x cubed plus, well, actually it becomes a minus. Minus 2 over 4 is 1/2, so minus 1/2, and then this is times 1 over x cubed. So an easier way for me to write this yet would be something like this. We could factor out the 1/2, and then we have x cubed minus 1 over x cubed. The reason why I'd recommend that, just because it's going to be easier when we square this, right? Rather than having to square all the 1/2s and all that stuff. So when we do this, we want to do 1 plus dy dx, the quantity squared, right? And we're going to want to take a square root of that soon enough. Notice I'm not even touching the integral. All this is algebra. I mean, we did a little bit of calculus to calculate the derivative, but so this is 1 plus, and now we have 1/2 x cubed minus 1 over x cubed, that quantity squared. Okay, so this is 1 plus 1/2 squared is 1/4. And now let's complete the square on that second part. So we get an x to the 6th minus, notice we have 2 times x cubed times 1 over x cubed. And then minus, so that makes plus 1 over x to the 6th again. Please let me know if there's questions at that part, because that's the tricky part on this and what's going to happen here. So in terms of how this sets apart, notice these x cubes cancel, and you have 2 times 1/4, so you essentially have 1 plus, you have 1/4 x to the 6th, and then it becomes minus 1/2, and then plus 1 over x to the 6th. No, 1/4 x to the 6th, sorry. But you can notice the 1 and the 1/2, these two things you can add together. So this thing equals, we have 1/4 x to the 6th power plus 1/2, right? Plus 1/4, and then it's 1 over x to the 6th power. Here's the tricky part on this one. This thing is a perfect square. And how can you tell that? Well, notice when we had this, we ended up squaring this component. Notice what happened. We had 1/4 x to the 6th minus 1/2, and then plus 1/4 x to the 6th. So notice this minus 1/2, let me circle that there, has now become a positive 1/2. And so the only difference is instead of a minus in this position where we square it, it's turned to a plus. And so with that being a plus, what this is we take a 1/2 out, and then we have x cubed plus 1 over x cubed. And that whole quantity is squared. So why is that nice for us? Well, when we look at it, notice we're taking the square root of all this. So the L equals the integral, our intervals from 1 to 2. We have the square root of 1/2 x cubed plus 1 over x cubed. And then we're going to square that quantity. Well, when you take the square root of a square, and we're on the positive interval, because we're going from positive 1 to positive 2, and all those values are positive, it just becomes a regular value. So this thing is the integral from 1 to 2 of 1/2 x cubed, let me slap a dx at the end of that, plus 1 over x cubed dx. So notice this is tricky algebra, right? So that's what we're trying to work with. And then this thing becomes 1/2 1 over x cubed, remember, is x to the negative 3. So when we do this, we get 1/2. This is x to the 4th over 4. Okay. So it becomes minus 1/2 x to the negative 2, evaluated at 1 and 2. That's just the reverse power rule there. And so now when we plug this thing in, we get 1/2 times, we'll get 2 to the 4th minus 1 to the 4th all over 4, and then minus 1/2. The next one's a bit trickier. I can't just do exactly what I did before. It goes 1 over 2 squared minus 1 over 1 squared, because we're going to have different denominators there. And we can leave it as is if need be. If not, if you don't like that, you can do, what do we have? 1/2. And so this will be 16 minus 1 is 15 over 4. Minus, so notice this is 1/2 times, this will be 1/4 minus 1. So that should be negative 3/4. So negative and negative should make a positive, and so we'll have 1/2 times, this will be 30 over 8 plus another 3 over 8, and so that should make 33 over 16 as our final answer. Big sigh, I know, that's a tricky one. But hopefully you can see how we have to really be sharp with the algebra on a lot of this stuff. That's what I'm trying to make sure that we're aware. The arc length ones are really technical with that algebra. You can't get away from it. You're going to have to know when those perfect squares show up to make your algebra easier. Otherwise, if you tried to integrate where we had this expanded out, extremely difficult, right? But if you recognize that that's a perfect square, life becomes easy. So, on area of a surface of revolution, what's happening here? Well, we did some revolutions around the x-axis before. So let's say we have a function right here, f of x. What we can do is we can kind of put its mirror image on the side and revolve this thing around. Okay? And so before, when we're talking volume, we're talking about, pretend this was right side up and we try to fill it up with water. How much water does it take? That's the volume. Now what we're trying to do is change the game. We want to say, okay, rather than that, let's try and figure out how much paint it would take to paint the outside surface. So talking about surface area in terms of what's going on. And notice what happens. You have an arc length show up right inside the function, and that's because you have a distance, and then 2 pi times, well, we want that radius, right, because we're revolving around in a circle, because that's our area, right? So when we take the radius going on here, that's going to be 2 pi f of x. So basically we take our length of our total distance, and then this is kind of behaving like a radius, and that's how we'll calculate it. We'll take this integral. Now, a little bit more technical, we can prove this, but I'm not so concerned on the proofs. I'm concerned about being able to use this formula. And so remember, I'll write it up here. When we tackle this, it goes 2 pi f of x times the square root of 1 plus f prime of x, the quantity squared, and then we have the dx. Okay? So in case you forget it, it's right there for you. Now, with the bounds, I'm not even actually going to touch, since we're revolving around the x-axis, everything's in terms of x, we're good to go with the surface area. So we don't even need to draw the shape. You can. It's not impossible to do. But so we have 0 to pi. I'll pull a 2 pi out in front. Write down the function, cosine of 1/2 x. But now the fun part, square root of 1 plus, well, we need dy dx. Right? And so notice we get dy dx equals, so this would be, the derivative of cosine is negative sine of, and then we have 1/2 x, but we need to use the chain rule, so that's going to be times 1/2. Right? So questions on that part, please let me know. And so this thing becomes 1 plus, we'll write this as negative 1/2 sine of 1/2 x, the quantity squared, and then we have a dx. So notice you can rewrite this thing as 2 pi, the integral from 0 to pi, and then we can write this as 1, oh, sorry, got ahead of the cosine there. Cosine of 1/2 x, square root of 1 plus, this would be 1/4 sine squared 1/2 x. And then we have a dx. So this looks nasty probably right now. So what we'll do to solve this from here is we'll use a u substitution. U equal to, and what makes this real nasty is that sine squared on the inside of that square root. So my recommendation would be let u equal sine of 1/2 x. So that means du equals cosine of 1/2 x times 1/2 and then a dx. So notice we have the cosine 1/2 x right here, and we have the dx, and so we can actually multiply both sides by 2 to get 2 du, equals cosine of 1/2 x dx. So the only other thing that we're going to need to do, so we'll have this thing equal to, if we're doing this and we aren't going to make it a general form antiderivative, we got to plug in the bounds. So we'll go sine of 1/2 times 0, so that's just sine of 0, and this one's going to be sine of pi over 2. Okay, and so now our new integral becomes the square root of 1 plus 1/4 u squared, which we'll talk about in just a minute, and then times 2 du. Okay. Any questions thus far? All right. So, moving forward from here, you can actually take that 2 du and move it on inside if you like. So notice 2 du is the same thing as the square root of 4 du, right? And so then you can multiply it on inside the integral. So you get 2 pi times the integral. Sine of 0 is just 0. Sine of pi over 2 is going to be 1. Now this is, remember, this is square root of 4, so we can multiply square root of 4 times each term. So this is the square root. 4 times 1 is 4, plus 1/4 u squared times 4 makes u squared, and then a du. All right. So now where do we go from here? Well, we actually have some options, dependent upon if you recognize what's going on or not. One option that we can kind of do is, if you remember the trig substitutions, you can let u equal to 2 tangent theta, and then du equals 2 secant squared theta d theta. So this is going to be a tough integral, I'm not going to lie to you. But so this thing equals, so actually, you know what, well, let's do a general, and we'll come back to that. So what we'll do is general square root of 4 plus u squared du. And so notice that becomes the integral of the square root of 4 plus, if I square u, notice that's a 4 tangent squared theta, and then we have a 2 secant squared theta d theta on the outside. And so this becomes, well, this is 4 times 1 plus tangent squared theta. And notice that makes secant squared theta. So if I take the square root of 4, that gives me an extra 2. So this becomes 2, and then the square root of secant squared theta is secant theta times the secant squared theta into d theta. Oh, I forgot the extra 2 here. So that becomes 4 times the integral of secant cubed theta d theta. Now if you haven't seen that before, that's fine, we can work this. The way you're going to work this problem is you're going to use an integration by parts sort of thing, but I'll actually need the extra page. So we'll come back to this in a second. So how do we do this? Well, you have a u equal to secant theta and a dv equal to secant squared theta. And this was done in an earlier broadcast for this. So just in case, you can always refer back to. If you get lost in the steps, let me know. I'm happy to help out best I can. So if you do all this, you have a setup where we can write this as secant theta tangent theta minus the integral of, notice you'll have a secant theta and a tangent squared theta, so secant theta tangent squared theta and a d theta. Okay, So tangent squared, though, if you remember, that should be 1 plus tangent squared theta equals secant squared theta. So this equals secant squared theta minus 1. So we have that the integral of secant cubed theta d theta equals secant theta tangent theta minus the integral of secant theta and secant squared theta minus 1 d theta. So notice this becomes the integral of secant cubed theta d theta equals secant theta tangent theta minus the integral of secant cubed theta, which you'll notice something d theta here, minus a minus, and we have that multiplied by secant theta, so that makes a plus, an integral of secant theta d theta. So now this appears on the other side, so we add it on over, making 2 times that integral of secant cubed theta d theta. And this equals secant theta tangent theta plus, we'll talk about the integral of secant theta tangent theta, or secant theta d theta, I'm sorry, in just a second. Because we get the integral of secant cubed theta d theta equals 1/2 times this whole quantity, secant theta tangent theta plus the integral of secant theta d theta. And the beautiful thing is we have a nice solution for that. It's going to be a natural log of secant theta plus tangent theta. That's one I'd recommend knowing. It's a tricky one in terms of what happens. So secant theta tangent theta plus a natural log of secant theta plus tangent theta. That's all sorts of nasty, but I'm going to use that. And there's a table of integrals where you can have that integral down pat too. So notice this thing becomes 4 times the 1/2 secant theta tangent theta plus natural log of secant theta plus tangent theta. 4 times 1/2 gives us 2. So 2 times secant theta tangent theta plus 2 times natural log of secant theta plus tangent theta. You might be saying, but Josh, what the heck where are we going with this? Well, we actually need some work to do still, and I'll do that in pink, because using this information right here, well, actually mainly this piece right there, you actually have u over 2 equals tangent theta. So that means you have a nice little triangle. You have theta sitting right there. It's opposite over adjacent, so it goes u over 2. And that means this is square root of 4 minus u squared. Okay? And so when we plug all this stuff in, we're going to have it back in terms of u. And so we'll have the 2 pi times, what does this integral become? It goes 2 secant theta tangent theta. So 2, what's our secant theta? Well, that's 1 over cosine, so that's the square root of 4 minus u squared all over 2 times tangent theta. Well, tangent theta we already know is u over 2. Okay? Plus 2 times natural log of secant theta, we already mentioned, is square root of 4 minus u squared all over 2, plus tangent theta, which we already mentioned is u over 2. Okay? And we've evaluated this thing at 0 and 1. Okay. So now, where do we go from here? Well, we get 2 pi. Not sure I'm going to be able to fit all this. So 2 pi times, notice our 2's will cancel here. Okay. And so when we plug in 1, notice we'll get the square root of 3 over 2 times 1/2. when we plug in 0, we're going to get 0 just from that term right there. So we don't even have to worry about the 0 for that part. Okay? So plus, let's worry about that next piece. We get 2, and then we have natural log. Plug in 1, you'll get square root of 3 over 2 plus 1/2. And you might be concerned because you say, oh, well, what happens when we plug in 0? Well, you get square root of 4, which is 2 over 2, so that's going to be 1 and plus 0. But the natural log of 1 actually equals 0. So our final answer closes off right there. Not pretty whatsoever, but you can actually do it. It just takes a lot of work with these integrals. Now, I chose tough ones for a reason, so you can see how the integration can get nasty. It can get easier as well. So just want you to keep that in mind when working some of these problems. All right, so that's what I have. I think, well, let's see. Do I have one more? Oh no, that was the secant cube business. So that's all I have for today. If you have more questions, if I didn't even respond to them all just yet, if you give me enough time on the YouTube Live questions on the discussion board, I'll be able to answer them next session and whatnot. Just make sure to include your work on those problems. So hopefully I don't see any more questions. If there are, please ask, and I'll be happy to kind of clear it up real quick if there's questions on these last couple problems. But otherwise, hopefully this helped, and hope you have a good rest of the night. Oh, you're looking at some of the past exam number 2s because those ones correlate to what we are doing now. Using it for practice, there are a few questions that are a bit confusing in the wording. Yeah, most definitely. Post those to the YouTube Live discussion, and I'll be happy to address those because basically what I do, I try and set up the questions ahead of time. So yeah, you can email me about them. You can do that. You can put them in the discussion board. That's great too. And as I said, I'll do another YouTube Live session, and I can address those questions there too. It takes me some time to set up all the, if you notice I already have the questions written down ahead of time, rather than wasting the time to be writing them down during the session. So if you email them prior to, say, an hour before the live broadcast is, actually 2 hours would probably be a little bit better because it takes me about an hour to just write up everything. If you give me that amount of time, I'll be happy to address those in the next YouTube Live session. So does that make sense then? But yeah, I'll be happy to address any exams, and just send me your work is the main thing. So I'll be happy to address all those. But yeah, I'll take a look. Okay, awesome. So yeah, if there's no more questions in regards to what you saw here, I'll be keeping an eye on those YouTube Live discussions, kind of address those. Just make sure, always include like your work on them. That helps me too to see what you know, and I can kind of clarify bits and pieces as I'm kind of going through it too. So especially seeing your approach. But hopefully that helped. If not, just ask more questions, and I'll try and do even more YouTube Live sessions. So hope you have a good night.